There we go. Okay, so welcome back. Today, we will start with acids and bases. So looking over the Alex homework for chapter 4, there's quite a few, a pretty large number of acid-base problems. And in the textbook, acid-base chemistry is actually a pretty small section in there. It's just a few pages. But acid-base chemistry is pretty important. So there's, 5 or 6 different types of problems here for acid bases. We're not going to go into great details about the chemistry of acids and bases. It's a fascinating topic and it's an important one. But the second course in our sequence, Chemistry 1200, that's where we spend quite a bit of time. There's actually 2 full chapters dedicated to acid-base chemistry. But here, really what we're going to do is just sort of like an introduction to what acids and bases are, how to kind of think about them and identify them a little bit. And then we'll move on into redox chemistry and molarity. Okay. So let me come over here. All right. So let me start with the first type of problem, which is just identification. How do you identify acids and bases? And what I'm going to do is I'm going to show 4 different categories of acids and bases, okay, just so that you have them. So the 4 different categories are what they call strong acids, and then weak acids, and then there's strong bases, and then there's weak bases. So kind of implicit in the name where we talk about things being strong or weak, there is actually some, hold on a second, let me come over here. There is actually a kind of an implicit idea that when something is strong, it's actually kind of powerful. There is that sort of aspect of it. So the strong acids are actually pretty powerful reactants that can be used to run chemical reactions. Same with strong bases. So when you go on to do chemical reaction, like making things, synthesizing things, often you'll use strong acids and strong bases to really like drive the reaction forward because they are strong. Okay. But technically the term strong really isn't like power. It's not about the power, how powerful this reactant is. It's really more about how it dissolves in water. So a strong acid dissolves into water and forms ions just like an ionic compound does. And the same is true with the strong base. A strong base, when you dissolve it into water, it dissolves into ions. And we'll talk about that in a moment. And so it behaves very much like an ionic compound. Okay. So let me put a list here. So the most common strong acids are HCl, HBr, and HI. So notice there's a hydrogen and then a non-metal. So that's a very common format for acids, is there's a hydrogen and then a non-metal. So HCl, HBr, HI. So you might say, well, what about H2O? Well, that's a hydrogen with a non-metal. And in fact, H2O is actually an acid. It can behave like an acid. H2S, that's a hydrogen with a non-metal. Yeah, that actually acts like an acid too. So those are 3 of them. Now there's also strong acids that have polyatomic ions. So there's HNO3. So nitrate is NO3 minus, that's the polyatomic ion. There's HClO4, and then there's HClO3. So there's 3 polyatomic ions, the nitrate ion, which is this right here, the perchlorate ion, and then the chloride ion. So those last 2, they're not real common. You're not likely to run into those in your everyday life. But nitric acid is a very common reactant, as is HCl. Now, HCl is really the acid that's active in your stomach. So your stomach is generally very acidic, and that acidity is to a large extent because it has HCl dissolved in it. It's a pretty strong acid. Okay, so those are strong acids. Then there are weak acids, and I'm only going to do a short list of weak acids because the number of weak acids in nature is probably in the tens of thousands, at least thousands. There's a lot of weak acids out there, but I'm just going to show you a few. So the first one is H2CO3. Okay, so notice though, the format's kind of the same. You have hydrogen and then non-metal. This one, notice it has, oh, I missed one strong acid. That's an important one. I'm sorry. H2SO4. That's called sulfuric acid. That's a very important strong acid, H2SO4. So there's 7 in that list. H2CO3. I could just keep going on. H2SO3. H3PO4. So again, but look at the form. Now you may have noticed that, like, hey, a lot of these have 2 or 3 hydrogens, and that's true. These are called polyprotic acids. They have more than one hydrogen. We could do HNO2, not NO3, but NO2. Okay, but you can recognize these as acids by looking at the formula, right? You've got hydrogen and then non-metal, and the non-metal is either an element or a polyatomic ion. So there's HCN, which is called hydrocyanic acid. There's H3PO3, that would be one right there. And then there's like all the amino acids, right? And so amino acids, so let me show you just kind of real quickly one amino acid, which is COOH, H, NH2. This one's called glycine. That's an amino acid. Okay, so there's many amino acids in nature. And then there's one more I want to show you, which is CH3COOH. So notice with this one, the H is at the end. It doesn't have to be written that way. It could be written in a condensed form, HC2H3O2. So here you're condensing everything and you're putting this hydrogen in the front just so that it kind of has the same formula like these ones do, the same format, okay? And like I said, there's many more weak acids than there are strong acids. These are just some of them. But for the most part, these are the common strong acids, okay? So generally, we do recommend that people memorize not the weak acids, but memorize the strong acids. Remember all 7. So it's ClBrI, those are the halogens, HNO3, HClO4, HClO3, and then H2SO4. And again, if it has 2 or 3 hydrogens, we call that a polyprotic acid, okay? So you're recognizing it as hydrogen with a nonmetal. Now, what about the strong bases? There's actually 7 of those as well. So LiOH, NaOH, KOH, RbOH, CSOH. So those are the alkali metals, the first column, 1A. And then let's do strontium hydroxide and barium hydroxide, BaOH2. So these are the lower, these are group 2 metals, strontium and barium. So group 1 and then group 2. They'll just put 2 of them at the bottom there, strontium and barium. So those are all strong bases. We'll talk about what these things do in a moment. And then the weak base, so again, I would at least memorize these first 5, the alkali metals with a hydroxide, OH. The weak bases are nitrogen based. So if you've heard of DNA, if you've heard of RNA, these are what we often refer to as nucleic acids, but they're also bases. So, and they all have nitrogen. So the idea here would be that you have a nitrogen with, sometimes with hydrogen like this. This is NH3, this is called ammonia. That's IA, ammonia. And then organic, so CH3 NH2, sorry, NH2. This is called methylamine. So if you heard the name amine or amino, that means it's a base. CH3CH2NH2. So see again, you got the carbon and hydrogen. So if you have carbon and hydrogen, and then you have N and H2, NH3, and many of the kind of chemicals that we ingest, like caffeine, nicotine, cocaine, morphine, all of those chemicals, they're all essentially weak bases with nitrogen. They generally are a nitrogen attached to carbon atoms, often in a ring. So you might have something like this. So this nitrogen right here, this would be a base because it's got the N attached to hydrogen and attached to carbon. So if it's attached to hydrogen or to carbon or to both, then it's most likely a base. Okay, and those are weak bases. All right. So you see these in things like morphine, cocaine, nicotine, caffeine. Sometimes people will wear a t-shirt with the chemical structure of caffeine. And if you look at it now, what you'll see is, oh yeah, there's some carbon atoms in a ring and there's nitrogen in the ring. And so that nitrogen right there is telling you that caffeine is a base. Bases, oh, just so that, you know, kind of giving you an overview, bases tend to taste bitter. Okay. So, you know, all of those chemicals like, you know, morphine and cocaine and caffeine, they're a little bitter. The ones that are strong bases are very bitter, but the strong bases are dangerous because not only are they bitter, they also react with fats, with lipids. And when they react with lipids, they turn the lipids into soap. So if you come in contact with a strong base, it will actually dissolve the lipids in your skin and then turn it into soap. So it'll feel soapy, but it's soapy not because, you know, it is a soap itself. It's soapy because it's turning your skin into soap. So then it's going to be painful at some point. Acids taste sour. And in fact, this one right here, which is called acetic acid. Okay. Acetic acid is the main ingredient of vinegar. So it has that sour taste, right? Candies often have what's called citric acid in them, or citrate. And that citric acid or that citrate is kind of soury tasting. So lemons and limes, they have citric acid in them, so they taste sour. So sour. Now, the strong acids are a whole different ballgame because they're so powerful that, you know, I'm not even sure they taste sour because they just start reacting with things inside you. So you don't want to ingest them at all. But the weak acids, these ones right here, you know, phosphoric acid, for example, that one is added to foods. You know, most of these are pretty dangerous. You wouldn't take this one. You know, this one's dangerous. This one's dangerous. This one's very dangerous. But phosphoric acid's not that dangerous in small quantities. Carbonic acid's not that dangerous in small quantities. The strong acids are, though, like, you know, HCl we produce in our stomach, but stomach has a lot of protective, you know, techniques for keeping it contained. Okay, so 4 categories: strong acids, weak acids, strong base, weak base. I recommend, this is what I recommend generally to people, is just remember the strong acids, remember their formulas. There's 7 of them. Remember the strong base formulas: alkali metals with the hydroxide, and then 2 of the alkaline earth metals with 2 hydroxides. Right? And then anything else that has a hydrogen in front of it, if it's not, it's a weak acid, right? Because if it's not one of those 7 strong acids, it must be a weak acid. So that way you don't have to memorize all the weak acids. You just memorize the strong acids. And then if it's not a strong acid, it's a weak acid. And then for the weak bases, just remember, oh yeah, if you have a nitrogen and it's connected to either hydrogen or it's connected to carbon or it's connected to both, then it's a weak base. And then you can actually classify all 4 of them. Okay. So let me show you an example from Alex. So what they do in this one is they give you 4 different categories. I'm sorry, they give you 4 different compounds. And then you got to determine whether they're ionic, molecular, acid, or base. Okay. Now, acids are considered molecular compounds because hydrogen is not considered an ion. I mean, it's not considered a metal. So if it's an acid, it's a molecular compound. So let's take a look at these here, okay? So let's take a look at the first one. The first one is H3PO4. Well, that one's pretty straightforward, right? You got this hydrogen in the front, and then you got a non-metal here, 2 non-metals, right? That's a polyatomic ion. So that right there, you know, is an acid. Since it's an acid, it's also molecular, okay? Second one, again, there you take a look at the formula. You got the hydrogen in the front, then you got these non-metals there, so that makes it an acid. They're not asking you whether it's strong or weak, so that's not the issue. And since it's an acid, it's a molecular substance, okay? Now let's get to the next one, NaCl. Now, is that an acid or base? Well, it doesn't have any hydrogen, so it's not an acid. It doesn't have any hydroxides, there's no OH. And it doesn't have a nitrogen with hydrogen or nitrogen with carbon. So that means it's not a weak base either. So it's none of those. It's not molecular, acid, or base. So it would be ionic, right? Ionic. This would be a metal with a non-metal. So that would be ionic. And then KOH. Now, here's a metal and a non-metal. So that looks like it's ionic. But remember, that's one of the bases, right? The bases are those 7 metals: lithium, sodium, potassium, rubidium, and cesium, with barium and strontium, okay? And so that's going to be a base, right? The question is, it's a base, but is it also an ionic compound, right? So that's an interesting issue. So the question is, what's an ionic compound? Well, ionic compound is a metal with a non-metal, right? So the KOH, not only is it a base, it's also an ionic compound, right? So keep in mind that something could be ionic but not a base, like sodium chloride, because it doesn't have the OH minus, the hydroxide. But if it is one of these, you know, KOH or NaOH, not only is it a base, it's also an ionic compound. Okay, so acids are molecular. The strong bases are ionic and bases. Okay. What about this one? What about NH3? Let's take a look at that one right there. If we just add that to the list, well, that one's a weak base, right? So if it's a weak base, it's still a base, but it's not ionic, right? It's not ionic because it doesn't have any metals. It's not Na, it's not sodium, it's nitrogen. That's a nonmetal. So if it's nonmetal with hydrogen, that means it's a molecular substance, right? So the weak bases like caffeine or ammonia, those are molecular substances. So all you're doing in terms of molecular versus ionic, really all you're doing is you're looking at whether it's a metal like sodium with a non-metal versus a, you know, a non-metal with, well, like this one right here. Non-metal, so that would be molecular, right? So if it's all non-metals, it's molecular. Now, there are exceptions to that. So the one exception that I can think of is this one. This is an unusual compound, but an important one. So this right here, you say, oh, that looks like a molecular because everything's a non-metal. But just like everything in nature, things are more complicated. This is actually an ionic compound because it's got the polyatomic ion ammonium and the polyatomic ion nitrate. So generally, it's true, metal with non-metal is ionic. But when you throw in those polyatomic ions, you can combine polyatomic ions in such a way that if it's the ammonium ion, that's an ion, right? And this is an ion too, so it is actually ionic. So just remember that ammonium is a polyatomic ion. So if you ever see that in a formula, NH4, the NH4 is going to be a polyatomic ion, and so that means that it's an ionic compound. Okay, let me close that one off. So that's identifying. Okay, and let me just see if there's any examples they throw in there that are different. Looks like it's all, that's pretty much. In fact, I'm not even sure they give you the nitrogen ones. Okay, yeah, so that's pretty much what I just went over. Looks good. Okay, so then the next issue is, before I go into this, is the issue of like what are acids and bases, right? So I said how to identify them. We looked at the formula, but what are they? What's an acid? Okay, so there's different definitions, interestingly enough, of what an acid and a base are. So there's multiple definitions, but I'm going to give you one right now. An acid is a substance that dissolves in water. Okay, so it dissolves in water. That's cool. And in that process, ionizes to form an H plus ion. Okay, H plus ion. And that H plus ion is called a hydrogen ion. Okay, it's called a hydrogen ion, right? So an ion, because it's charged and it's hydrogen, it's a monatomic ion. It's also called a proton, right? So the term proton or protic, we use that a lot when it comes to acids. And why is it called a proton? A hydrogen atom, right? If you look at a hydrogen atom, it's got a proton in the center, and it's got an electron orbiting the proton, right? So that's the proton at the center. It's the simplest element in nature, right? The simplest element in nature is hydrogen. One proton, one electron. Hydrogen is easy to actually like make calculations on because it's such a simple system. But what happens when you have a hydrogen ion? You take the electron off, you remove it. So if you remove the electron from a hydrogen atom, what are you left with? You're just left with a proton. That's the only thing left. It turns out it's very energetic. You take the electron off of a hydrogen atom, it becomes very energetic and will do all kinds of interesting things. But that's why we call it a proton. A proton is just a hydrogen atom that's lost its electron, or it's called a hydrogen ion. Okay, so that's what, so anything that does that. So for example, HCl. If I take, HCl is actually a gas in its pure form at room temperature. At room temperature and atmospheric pressure, it's a gas. If you put it into water, meaning bubble it in, you just take a little tube and bubble some of this gas into the water, it will react with the water, and what you get is H plus dissolved in water and Cl minus dissolved in water. You get hydrogen ions or protons and chloride ions. So that means it's an acid, right? That tells us it's an acid because it's forming the H plus. What else could, what's another example? Another example would be this acetic acid. This is one of the weak acids. Okay. Now, acetic acid is very difficult to make it pure. It's so attracted to water that in the factory, it's very hard to get all the water out. So generally, it's like 97, 98% acetic acid, and still a little bit of water in there. It's really hard. You can't get that water out, essentially, at least not easily. So it's a liquid, though. And if you dissolve it into water, it essentially does the following. It dissolves and ionizes. So here's your H plus, right? This is the H over here. So that's why it's kind of drawn that way. Here's your H plus, here's your H plus. So that means it's an acid, right? This is acetic acid because it's forming this H plus ion in the water. So that's what makes it an acid. Acetic acid is a weak acid. Hydrochloric acid is a strong acid. Okay, what does that mean? What that means is if I put in 1 mole of HCl into the water, into a big pool of water, it will ionize 100%, meaning that 100% of it will break up into ions. So you'll form a mole of this and a mole of that. A weak acid only ionizes a little bit, maybe 1%, maybe 0.1%, maybe 0.01%, maybe 2%. Only some of it ionizes. So if you put in a mole of this into the water, you might only get 0.1 mole. Or actually it's even less than that. Acetic acid is weaker than that. 0.01 mole. 0.01 mole. So that's why a strong acid, we call it strong because it's a strong electrolyte. What happens is if you put in a mole of this, you get a mole of these ions and another mole, 2 moles of ions. So that's going to conduct electricity really well. Ions conduct electricity if they're able to move around in water. But this one, you're only going to get a little bit of ions, a very small amounts. So it's not going to conduct electricity very well. So it's a weak electrolyte. It's a weak acid. Okay, so that's what an acid is. That's one definition. Another definition of an acid is it's something that if you put it in water, it reacts with the water. So it's actually a reactant. So it's not just dissolving in water, it's actually reacting with the water, and it is transferring. It's actually transferring the H plus, the hydrogen is actually getting pushed onto the water. So you lose the hydrogen ion on the chloride. So it's now all by itself. And now the water has that extra hydrogen in the form of an ion, right? So it's really transferring an H plus. H plus is what's getting transferred there. And so this is called the hydronium ion. Okay, so if you ever see that word hydronium, it's H3O plus. That's the product of the reaction between the acid and the water. So water will absorb or accept that H plus. It's a transfer reaction, and that's what you'll have. Okay, let me just put my headphones in here. Yeah. Construction next door. All right. Hopefully that'll work a little bit better. Okay, so that's another definition. And actually, if you look it up, they call that Bronsted. Bronsted-Lowry. That's the Bronsted-Lowry. We cover that much more in Chemistry 1200. We just going to introduce it here, this idea today. This kind of idea that it forms an H plus, that's what an acid is. It forms H plus. That is called the Arrhenius theory. It's a pretty old theory. It was created by Svante Arrhenius, like, I don't know, 150 years ago. Yeah, about 150 years ago. Smart guy figured out, hey, these are ions. These are little charged particles that are moving around in the water. Okay. So this one's pretty useful. It's a useful theory. This is useful also, but it's something that you'll use more of when you move on to more advanced courses if you do that. Okay. So most of the analysis you'll see is like this and a little bit of like that. Okay. So that's an acid. What about a base? The base is kind of similar. So a base is a substance dissolved in water that forms, or produces, you could use that word, produces the hydroxide ion. Okay, so let me just make a little list here. You got your H plus, that's called a hydrogen ion. You got your OH minus, that's the hydroxide ion. And then you got your H3O plus, that's your hydronium ion. In general, if something ends in IDE, it's negative. Cyanide, chloride, bromide, hydroxide. If it ends in IDE, it's negative. If it ends in IUM, it's positive. So Hydronium, ammonium, in some parts of the world, aluminium, right? It's an aluminium. They call aluminum aluminium. So dissolved in water, aluminium is positively charged. Beryllium is positively charged if it's dissolved in water. Okay. So IUM is positive, IDE is negative. Okay. So examples, pretty straightforward. NaOH. It's a solid. As a pure substance, it's a solid. And if you dissolve it into water, you get this ion, this sodium ion, and then you get the hydroxide ion. Oops, not ON, OH. Okay, so hydroxide, there's your hydroxide ion. Now, I keep forgetting, I think, the hydronium ion has a different name if you're in different parts of the world. I forget, it's like hydroxonium or something like that. But in the States, we call it hydronium, H3O plus, okay? That's not an N, by the way, that's an H, hydroxide, okay? So anything that produces the hydroxide ion is a base. If it produces a lot of it, so if I put in a mole, and when it dissolves, you get a mole, then it's a strong base. So that means it's strong. But there are weak bases also. Remember, the nitrogen bases are weak bases. So let's look at that one. Here's ammonia. This is a weak base. As a pure substance, it's a gas at room temperature and 1 atmosphere pressure. If you bubble it in as a gas into water, then what happens is, this is interesting. What happens? You get 2 new ions. You get the hydroxide ion. But where did that come from? Where did you get that? That is not even a balanced equation. You've got oxygen on the right side, but not the left. What happened there? Okay. Well, first of all, if you put a mole of this in, you're going to get like 0.01 moles of these. Okay, so you won't get very much of them. It's about, it's 1% ionization. But where does that oxygen come from? Where's that hydroxide come from? It comes from the water. So this weak base is kind of like the Bronsted-Lowry theory, which is this idea that an H plus ion is being transferred. So really what happens with the weak bases is they react with the water. So what happens is the H plus is transferred to the ammonia. So the H plus from the water. So now you add that H plus to the ammonia and you got NH4 plus, right? NH3 plus H plus. I'll write it out separately just so you can see how that came about. Okay, so you bring along the extra hydrogen and the charge. So there's your ammonium ion. This is called ammonium. Positively charged, right? Then what happened? The water lost the H plus. So it lost this. So that's gone. So it's just hydroxide left over. So in terms of acid-base chemistry, it's actually useful to think of water as H plus attached to an OH minus. Water's a pretty stable molecule. It doesn't generally break up, but you can make it break up by adding certain reagents to it. So if you add the ammonia to the water will react with the water. The water will essentially transfer an H plus to the ammonia. And in that process, the water is now converted into a hydroxide. That is Bronsted-Lowry chemistry because you're talking about the transfer of an H plus ion, okay? So that is Bronsted-Lowry. So that's how we can show that something that doesn't have the hydroxide in its formula, NH3, that's how we can show that it will, in fact, if you add it to water, it will make the water basic. So if you then drink the water, the hydroxide would make it taste bitter. But of course, there's also an ammonium ion in there, and ammonium is it's pretty toxic, right? So you wouldn't want to drink that water because of the ammonium, but the hydroxide would make the water bitter, okay? Same thing, it's only 1% of it, so 0.01 moles. Very little of it will actually ionize, but some of it will. It's not a negligible amount, because 0.01 moles, remember a mole is 6 times 10 to the 23rd molecules or ions. So 0.01 moles would be 6 times 10 to the 21 ions. That's a lot of ions, okay? Even though it's only 1%. So be careful when you see these percentages. 1%, oh, it's only 1% impurities. Well, 1% impurities could be 10 to the 21 molecules. Even 0.1% is still 10 to the 20 molecules. So these things can still be pretty important, even if the percentages are pretty small. Okay, so there's your 4 categories, right? You got your strong acid, you got your weak acid, you got your strong base, and you got your weak base. And there's 7 strong acids you want to memorize, and there's, I guess it's 7 strong bases you want to memorize, and then you got your weak acids and your weak bases, and then you're set. So those are our 4 categories. Okay, all right. And that's sort of like a little intro. So now here's what we want to do. We want to predict the products. By the way, we don't talk about pH in here in this course, which is a little bit odd. The issue is that pH is generally covered in the 2nd semester. But I may actually just mention it real quickly, because those of you that are biology majors, you're using pH all the time. So I will show it to you real quickly. The term neutralization often refers to what we call acid-base reaction. Technically speaking, neutralization is more broad than that, but in this context, we mean acid-base reaction. So that means you're reacting an acid with a base. Those are your 2 reactants. And the question is, what are the products going to be? In general, there's 2 products. It is very common that what you get is a salt and water. Okay, so we can't claim that this is always the case. You're always going to get a salt and water, but that's a very common process. And what do we mean by a salt? Well, technically, the definition of a salt is that it's an ionic compound that's produced from the reaction of an acid and a base. So that's kind of a circular argument. But a salt is typically an ionic compound. So an example of an ionic compound would be NaCl. And in fact, we call that salt. We call that table salt, right? NaCl is salt. So here, salt is more broad. It could be KCl. It could be RbCl. It could be BaCl2. But it's essentially an ionic compound, okay? And then we all know what water is, okay? So let me show you an example here. The one that I see here on Alex, they give you HClO4, and you react it with KOH. Okay. All right, well, what do we have here? We have a strong acid with a strong base, right? So notice, like, I immediately started in my brain categorizing these. This is one of the 7 strong acids. KOH, oh yeah, that's a strong base. So not only am I saying, hey, it's an acid and a base, I'm indicating that it's a strong acid and a strong base. For this particular problem, it's not that important that you know that, but it's a good idea to kind of get into that, particularly if you're going to take more chemistry. Okay, if it had been HNO2, HNO2 is a weak acid. And if it had been, NH3, that would be a weak base, right? So not only did I categorize NH3 as a base, I called it a weak base. But for this one, it's not particularly important. Now, here's what happens. If you remember when we did precipitation reactions all that long ago, right? We did it a long time ago, like Monday. We talked about this idea of double displacement reactions or double replacement reactions. These kinds of neutralization reactions are also double replacement or double displacement, which means that you've got two parts. You've essentially got H plus with a negatively charged ion. And then you've got a metal plus attached to the hydroxide ion. And here's what happens. Double replacement or double displacement means the H plus is the first part. It is going to combine with the second part of the second reactant. That second part happens to be a hydroxide ion. So really you've got H plus plus OH minus, which is the same thing as water. So you get water. I'm going to write water as the second one. Water's a liquid, by the way, at room temperature and atmospheric pressure. But what about the first one? Yeah, the first one over here. This is where your salt is going to come in, right? So this is your water. Now we have our salt, okay? M plus A minus. But in this case, the A minus is ClO4 minus. So it's K plus and ClO4 minus, that's just KClO4. Remember potassium, soluble in water. Okay, aqueous, right? If something's soluble in water, we write it as aqueous. So that's KClO4, there's your salt. So remember, a salt is more broad than just NaCl. A salt is the product of the reaction between an acid and a base. It's one of the two products. I actually heard that on a game show when I was a kid. And I don't think anybody on the game show got it right. They said, you know, the product of an acid-base reaction is, and the answer was a salt. I was like kind of amazed that that was on a game show. It wasn't on Jeopardy. It was on like some other show with celebrities. But I didn't understand that until I took chemistry. So there's your salt, right? So KClO4. So it's actually very useful to kind of go back and think about those polyatomic ions. You know, remember the polyatomic ions, which are, I went over some of them. These, you know, all these polyatomic ions, if you combine them with an H plus, you get an acid. That's really what an acid is. It's an H plus attached to one of these polyatomic ions or one of the monatomic ions like Cl minus or F minus or Br minus, right? So let's take a look at another example. So here's one HNO3. Here they don't put the states of matter, so I'm not going to put them in here. This one's a little trickier because you're using barium, but it's the same idea essentially. So you're going to get two products. Okay. Again, think of it as two parts. These are often what we call binary compounds. So an acid is the H plus attached to the polyatomic ion, NO3 minus. And then the base is the metal ion attached to the nonmetal, which is hydroxide. But there's two of those hydroxides, right? Two of them, okay? So what that does is it affects how you balance the equation, but the same idea. You take the H plus, you combine it with one of the OH minuses, so you get water, right? So you're doing this, AH plus OH minus equals water. Don't worry about that there's two, we'll deal with that separately. Then you take your barium, which is +2, and you combine it with your nitrate, that's your salt. But you can kind of see there's a problem here, right? This one's +2 and this one's only -1. So you need two of the nitrates, right? Because remember, if you have something that's +2 and you combine it with something that's -1, that's no good. That's not neutral. So you need another -1. So you need two of the -1s. So really what you're doing is barium with two nitrates. And we're writing that as BaNO32. So you still have to balance the charge by adding more of the polyatomic ions. Now we balance it. It's almost balanced there. The only issue is you've got, you know, two, well, let's look at it this way. You've got two nitrates, right? Two of the nitrates. So you got to have two of the nitrates on this side. So just put a 2 there, okay? That's going to give you the two nitrates. But by having two nitrates, now you've got the issue with the water. What happens is, if you count up your hydrogens, there's two H's here. And then over here, you've got two H's. So that's 4 hydrogens on the left side. You've only got 2 here, so put a 2 and you've got 2 waters. So when you're using the second column metals, you're going to have 2 hydroxides. If you have 2 hydroxides, you need 2 of the acids because you need 2 of the H pluses. And if you have 2 H pluses and 2 OH minuses, you're going to get 2 waters. Okay. That one's a little trickier just because of the numbers. That one's an easy one. So that one's there. Let's try this one. HCl plus CaOH2. Okay. Group 2 metal hydroxide. Group 1 or group 2 is a base if it's with hydroxide. In fact, think about the name. Actually, you know, it's like it just hit me. The names of those metals. Alkali metals. Alkali means basic. It means base. So really, when they came up with that name, what they were saying was, if you put that metal into water, you get a basic solution. It's a base. So we call it alkaline solution. You've heard of alkaline batteries. Alkaline batteries are batteries that are basic. The actual paste inside has hydroxide ions, and that's what drives the chemistry, or part of what drives the chemistry. So alkali metals. And then the next column, these are called the alkaline earth metals. I guess earth because you get them from the earth, right? I guess. But these are called alkaline. Alkaline, same thing, basic. You put these into water, you get a basic solution. Compare that to iron. If you put iron into water, you don't get a basic solution. It's not a base. So these metals are basic, meaning that they form the hydroxides. So alkali metals, alkaline earth metals, they both form basic solutions. So that's why they react with the water to give you a hydroxide compound, and those are basic in water. Okay. All right. So how do we deal with this one? Again, think of it this way. The H plus is going to combine with the OH minus. So that's the easy part. Now, what you could do is you could say, look, dude, we got 2 of those hydroxides, so we need 2 of the acids to give us 2 waters. So you can balance it that way too. That will work. You know, however you want to balance it is fine. But if you have 2 hydroxides, you're going to need 2 acids to form the 2 waters. That will actually balance it right there. And then what happens? Now you take your calcium and you combine that with your chloride. That's the nonmetal. So CaCl. But be careful. Calcium is in group 2, so it's +2. Chloride is in group 7, so it's -1. Sorry, -1. So that means you need 2 of the chlorides. And there you go. There's your balanced equation. Okay. So there's not a whole lot of them. You know, it's really, there's only 7 acids, and there's really, you know, it's really 9 bases if you include calcium and magnesium. So there's not a whole lot of combinations. So when you go through the Alex problems, you may see the same problem, the same reaction more than once, just because there's not a whole lot of possibilities. But those are acid base. So that's how you write. Remember, it's double replacement. You're thinking of it as 2 parts, but you just, the issue here is you got to know what their charges are. If you don't, like if you didn't know that chloride was -1, and if you didn't know that calcium was +2, it's going to be a struggle for you, right? You got to know these charges. So we're thinking it sort of like as H plus Cl minus plus Ca2 plus
with chloride and then another chloride, right? There's two chlorides. So then you're just saying, hey, what's happening? Well, this H plus, I'm sorry, not chloride, OH minus. This H plus is going to combine with that OH to give us a water. So we need another one to combine with this one. So you need two, right? So now you're going to have the other one combining with this one. So you're going to get two waters. And then your calcium is going to have to combine with the chloride. You've got two chlorides. So you get CaCl2. Okay. So just kind of practice those. You know, it may be unfamiliar type of stuff to you. You're not doing calculations. You're just sort of recombining these things. But think about it. That's what chemistry is, right? You're taking these atoms and you're recombining them. What was it? I was watching some science fiction show last night, and you know, this one creature was saying to the human, like, I could transform you into something different that's not human. What do you want to be? Right? And she's like, you can just do that? And she's like, of course, it's just atoms. All I got to do is reassemble the atoms and you're something else, right? If you think about it, if you took your body and you somehow had some machine that could reassemble the atoms, you know, you could turn yourself into a dinosaur, right? So that's essentially what's happening. These atoms are just recombining to form new substances. Okay. All right. Now this topic here is not really specifically about acid base, but it's really about classifying. So I'm going to call this, the title they give is Identifying Precipitation, Combustion, and acid-base reactions. I like this one because it kind of, you know, like we should have a big kind of overview of what's happening. Like we should understand not just the kind of nitty-gritty details of charges, but we should also kind of have like a big picture. Hey, what kind of reaction is this, right? And, you know, I remember taking like a pretty advanced chemistry course in college, and the professor asked the class, like, how big is an atom? And no one knew the answer. And he's like, hey, you guys are like taking advanced courses and you don't even know how big an atom is, right? So the answer is just an angstrom. An atom is approximately an angstrom. So we should have kind of a big picture of what's going on as well. So what's tricky about this problem is they give you so many possibilities, it's easy to kind of lose track of the categories. So they give you 7 different possibilities. Now they're using the term replacement, not displacement. And precipitation, combustion, and then acid base. So you have all these options. So actually what I'm going to do is just, I think it's easier if I come over here and I'm just going to go ahead and share the screen. So let me stop share this one and let me just come over here and share this screen because it's a lot of writing. So I want you to be able to see it. Oops. There we go. Okay. There we go. So now you can see that a little bit better. So they give you 4 different reactions and then they say, what type of reaction is this, right? So the trick to this is that more than one option is possible. It could be more than one category. Something could be a single replacement and be a combination, for example. Something could be a double replacement and be an acid-base reaction, or a double replacement and a precipitation reaction. A combustion could be single replacement, but generally it's not. But let's take a look. So let's look at the first one. So how do we deal with this? Well, the first thing I would say is that you should memorize the formula, not the formula, but the general format of a combustion reaction. The combustion reaction is one of the most important reactions in nature for us. Combustion is the reaction that we use to metabolize energy, right? So combustion is essentially what we do when we digest food. It's essentially anabolism, right? It's a form of metabolism. So that's combustion. Combustion is the opposite of photosynthesis. Combustion is how we generate energy from fuels. So when we burn a candle, that's combustion. When we burn oil or gasoline, that's a combustion, right? So combustion is important. Combustion is this: a compound that has carbon and hydrogen. Now, it can have other elements too. It could have oxygen, it could have nitrogen, but it's got carbon and hydrogen. We call that a hydrocarbon, reacting with O2 to form carbon dioxide, CO2 plus water. The amounts don't matter. So if it's 2 waters, 3 waters, 2 oxygens, 3 oxygens, it doesn't matter. As long as it's CH plus O2 to give you CO2 and H2O, that's combustion. So if you look at the first one, the reactant is CH3, right? So that's got hydrogen, it's got carbon. So that's a hydrocarbon, organic compound. It's reacting with O2 to give you CO2 and water. That's combustion right there, okay? So the organic compound could be simple like CH4, or it could be more complicated like CH3O, CH3. But as long as it's reacting with O2 to give you water and carbon dioxide, that's a combustion reaction. So that's combustion. Now it's also what we would call a redox reaction, but we haven't covered redox chemistry yet. So that's not in our category. Once we get through the next topic, we would say, oh yeah, I would also identify that as redox, but you don't need to worry about that right now. It is not a decomposition. Decomposition is actually covered at the end of chapter 3, as is combination. Combination is when things combine to give you something more complicated. Decomposition is when you take something that's complicated and it breaks up into things that are more simple. So that right there is not a decomposition or a combination. And so it would just be combustion. The second one, that one's pretty obvious, right? Look at that second one, HCl, that's an acid. NaOH, that's a base, strong acid, strong base. That's got to be an acid-base reaction, right? So we know it's acid-base. But remember, those acid-base reactions are also double displacement or double replacement. So for that second one, you would select off double replacement and acid-base. Third one, CH3CH3. Oh, there's your hydrocarbon. O2, there's your oxygen. CO2, carbon dioxide, H2O, there's your combustion. So you got another combustion there, right? So COMB, combustion. Last one, Na2S. Okay, well, it's not an acid and it's not a base, so it can't be acid-base. So what is it? Well, let's look at it again. Let's look at the states of matter. See how it's aqueous plus aqueous gives you aqueous plus solid? Jog your memory a little bit back from Monday, right? Aqueous plus aqueous to give you a solid plus aqueous, that's a precipitation reaction, right? So you're taking things that dissolve in water, you're getting something that precipitates out a solid, which is FES, so that's a precipitation reaction. But precipitation reactions are also double replacement. So if you have your Na combining with your Cl minus, Na plus Cl, and you take your Fe, you're combining it with an S, you're really doing that double replacement reaction. So the last one would be precipitation, but it would also be double replacement. Okay, let's see, did they do any? I want to see if there's any that are decomposition or single replacement, I guess. Let's see. So first one, that looks like a precipitation. Second one, that looks like a precipitation and double replacement. Third one's combustion, just kind of like we did earlier. But let's look at this last one. This last one is K plus S to give you K2S. So you're taking two elements, you're combining them to form a compound. That's called combination. Combination is when you take something very simple, combine it with something that's very simple to form something that's more complicated. K2S has two elements in it, so it's more complicated. So you're combining things. So that would be called a combination reaction, okay? Decomposition would be the opposite. If I just wrote the arrow in the opposite direction, K2S gave you K plus S, 8. That would be decomposition, Okay. I want to show you one that's a single replacement because we haven't seen any of those yet. But first one there, look at that one, that first one, that's decomposition, right? Something more complicated breaking up into two things that are simpler. That's decomposition. The last one down at the bottom, you're combining simple things to make something more complicated. That's combination. But there's no single, I don't see any single displacement or single replacement. So let's see if we can find one. They don't seem to give you a lot of single replacement in there. Maybe nothing will come up. Let's see. Yeah, I don't see any. So you may not get a single replacement. It's in there as a category, but it might be just an oversight that they don't put it in there anywhere. Okay, I'm going to show one more. Yeah, there's a decomposition, there's a combustion, there's a precipitation, there's a combination, but I do not see any single replacement. So let me show you. I'll stop the screen share and just show you just so you can see it. So single replacement. We'll actually see these when we get to redox chemistry tomorrow. So single replacement is where you take something that's kind of simple, like an element. So you got an element here. And then, let's do it this way, MB. So now you got a compound. And what happens is the element displaces or it replaces the other element. So what'll happen is, I guess let's do it this way, this over here. The B will combine with the A. So you get AB plus M. Right? Does that make sense? So here would be an example. An example would be something like Fe solid plus AgNO3 aqueous. And then out of that, you're going to get Ag solid plus FeNO3 2 aqueous. Okay, so let me just make sure I've got it balanced. Okay, so take a look at what happened. You got an element, and then you got a compound. And then at the end, you have an element, but it's the other element, right? So instead of it being the iron, now it's the silver. So the silver is essentially replacing, I'm sorry, the other way. The iron is replacing the silver. They're both competing for nitrate. Now the iron has the nitrate, so it's replaced the silver. So the format is an element plus a compound gives you an element with a compound, but the element, the new element, you know, is this one that started off by itself. Okay, so the iron, technically it's displaced. They call it replaced, but it displaced the silver. And that's called a single replacement. And it turns out single replacement reactions are an example of redox chemistry. It's reduction oxidation, which we'll cover tomorrow. Okay, so there you go. So that particular problem is really not acid-base chemistry problem. It's really just kind of like an overview of what we're doing with, you know, all of the reactions that we've looked at so far, all the possibilities. Okay. The next one I want to take a look at is this idea of, again, let me come back here. I think it's, you know, some of these problems are so lengthy in terms of their description that I just want to show you what it looks like, just so you can see it. Okay. So some of these, you know, this particular problem is identifying acids and bases by their reaction with water. Okay. So it looks, you know, it looks pretty intense here when you look at this table. There's a lot of stuff to fill out here, right? So it says in the problem that some chemical compounds are listed in the first column, right? So the formulas are listed in the first column. And they're going to tell you everything in here is soluble in water. So everything's going to dissolve into water. So we don't have to worry about this being some molecular compound that's not going to dissolve. Imagine that a few tenths of a mole, so a little bit of the compound is dissolved in the water, a liter of water. We'll start doing calculations in the last section. The important chemical species that would be present in the solution are written in the second column. So use the check boxes to classify each compound. So they're telling you what it dissolves into. So you're just trying to figure out whether this is an ionic compound, a molecular compound, a strong acid, a strong base, a weak acid, or a weak base, right? So that earlier discussion of strong versus weak is an important one, okay? So what they're saying is there's a lot of this in the water. So there's a lot of K plus, there's a lot of OH minus, and there's a lot of water. The water is not particularly important here because everything here is in water. That's the solvent. So it's just listed there to be complete. Okay. So let's take a look at the first one, K plus OH minus, and NH2O. So if you take KOH and you put it into water and you get K plus and you go OH minus, well, that tells you, one, it's ionic, right? It's dissolving to form ions, so it's an ionic compound. But it also tells you that you're getting hydroxide, and anything that forms hydroxide is a base. So that means you're talking about a base. Then you ask yourself, is it a strong base or is it a weak base? Well, remember there were 7 strong bases: lithium, sodium, potassium, rubidium, cesium, strontium, and barium. So that's potassium, so that's a strong base. So right there, you know that one's ionic and it's a strong base. Remember, the acids are molecular, even though they do form ions, they're molecular, and but they could be strong or weak. So let's take a look at the second one. Second one, there's no H plus, there's no H3O plus, there's no OH minus, so it's not an acid or a base. So you don't have to worry about being an acid or base. But there are ions. Na plus is an ion, ClO3 minus is an ion, so that means it's ionic. So NaClO3 would just be an ionic compound. The third one, NH3, you put that in, you get NH4 plus, OH minus, NH3, and H2O. So how do we identify that? Well, first of all, it's got an OH minus. That means it's a base. But it also has the NH4 plus. So this is the one I gave you earlier, right? The NH3 gives you NH4 plus OH minus. And we said that that was a weak base. So looking at the symbols there, you can't tell it's a weak base. That's one you just have to remember. NH3 is a weak base. So put it down as a weak base. Is it ionic? This is tricky. Even though it's forming ions, it's actually considered, just like the acids, it's considered a molecular substance. So the weak bases are molecular. All the acids are molecular. It's just the strong bases are ionic, and then ionic compounds are ionic. So that one would be molecular weak base. Now, HF is a little tricky because I didn't give you HF. You can be very easily confused into thinking HF is a strong acid, but it's not. The strong acids are HCl, HBr, HI. HF is excluded from that category. It's a weak base. So see how you got the H3O plus? That tells you it's an acid. But it also has HF. So actually, that's actually the clue. NH3, they tell you NH3 is in it, and they tell you in HF is in it. That's what tells you it's weak. Because if it were strong, there wouldn't be any of the reactant left over. So let me come back to that. Let's come back over here. So the weak acid and the weak base. So here's a weak acid, HNO2. That's a weak acid. What happens is, again, you put it in the water. It donates the H plus, so you get your H3O plus. So that tells you it's an acid. If you see H3O plus, that tells you it must have been an acid. And then you get your NO2 minus. What we said was, if you put a mole in, you only get like 0.01 moles. That means it's weak. So in that particular problem, the fact that they told you that you had HF and you had F minus and you had H3O plus, that's telling you it's a weak because there's still some of this left over. If they had said, hey, you just got F minus and H3O plus, there's no HF, that means it must have been strong. Okay, so HCl, for example, if you put that into water, you get H3O plus and you get Cl minus. So the only species you're going to have in the water are the products. You're going to have this and this. You're not going to have this in the product because it's strong. Why? Because if you put a mole of this in, you get 1 mole of this out. So there's none of this left over. Let me show you a little ice table. This is something you do in the next course, but it might be helpful for you here. HCl, strong acid. We know that's a strong acid. So essentially what we're saying is, like, initially at the beginning, you have a mole and these are 0. Then what happens is it reacts. So you lose a mole of this and this goes up by a mole. And so that at the end, we call this initial change and end. Initial change end, ice. Now, if you start with a mole, but you lose a mole, you get 0. So there's none of the HCl left. So in that table, if they don't show you the formula for the acid or the base as one of the species available, that means it was strong. And so then the products, 0 plus 1 is 1. 0 plus 1 is 1. So for strong acids and bases, okay, you're going to have the products present, but not the reactant. The reactant won't be present because it's 0. It's all gone. But for a weak acid or base, what happens is, let me erase this. So an example would be like HF, that one we just did, or the one from the table. The way this differs, it's still an acid, but the way it differs is if you start off with a mole of this and you don't have any of that at the beginning, you only lose like a little bit of it, 1%. And this goes up by 1%, right? So it goes up by 0.01 moles. And so then at the end, you still have 0.99 moles, right? 1 minus 0.01 is 0.999. So you still have the acid left over, but you also have this one. So these went up a little bit, but this only went down a little bit. So if they tell you, hey, you've got F minus, H3O plus, oh yeah, great, that's an acid. But if they tell you you also have HF present, that's what tells you it's a weak acid or a weak base if it happens to be the NH3, okay? In this particular case, you're just going to have your H3O plus and your Cl minus. That's what tells you it's a strong, okay? And it's kind of cool. Like, again, you'll cover that more detail in Chem 12 if you take that course. That's where we kind of go through the nitty gritty of the calculations. But really, you can't really understand what a strong acid or a strong base is unless you have this concept, which is a strong acid only, all of it is going to react. So you're losing all of the reactant and converting it into products. So that way, at the end, you don't have any of your reactant left over. Essentially, the HCl is a limiting reactant. But in terms of a weak acid, only a small amount of it reacts. Now, it could be, 10%, so that would be 0.1 moles, but it's not going to be 100%. So that means at the end, you're going to have some of all 3 of these are going to be there. And if you have all 3 of them present, that's what makes it a weak acid or a weak base, either one. Okay. So there you go. All right. let's see, it's just about time, but I have one more. I wanted to see if we could go over this one. Oh, okay. So we kind of did this already. How is this even any different than the previous one? Okay. Wow, I thought that was the same kind of problem, but that's okay. Well, here they want the states of matter. So I'm just going to show you this real quick. Let me come over here and go to share. There you go. Okay. So to me, it seems like the same kind of problem we just did, but it says here, predict the products of the reaction below. Now, this is for a strong acid with water. So for this particular problem, read the question, read the category, strong acid. That tells you that you're starting with a strong acid. So complete the right hand of the chemical equation and be sure it's balanced. Okay, that's cool. And make sure that it contains the state symbols. State symbols meaning aqueous or liquid. Ions are aqueous. So if it's, if it's an ion, it's aqueous. But you also have to consider, ions are aqueous. So for this one, you just need ions. So actually, now I understand. So with this one, what they're doing is they're having you apply the Bronsted-Lowry theory, which is forming the hydronium ions. So earlier I said mostly we do Arrhenius. I think that's actually, I have to retract that statement. Under the Alex problems, they're going to have you do the Bronsted-Lowry here. So this is an example of Bronsted-Lowry. Okay, so let me show you how to do this one. So actually, you're getting some good chemistry here. Bronsted-Lowry is a better way to do it. So here's what they do. They give you the reactants, and they're telling you it's a strong acid. But we knew that already from memorizing the 7 strong acids. Okay. So see how it's reacting with water? This is the power, this is like the amazing thing about water. Water is the most amazing compound probably in the universe, as far as I'm concerned. One, it's less dense as a solid than it is as a liquid. That's weird. Most compounds, when they solidify, they're more dense. But water, because of its crystal structure as ice, and there's different forms of ice actually, but water is less dense as a solid. Ice is less dense, so it floats. So, as you know, that's one of the reasons that animals can survive in the ocean, right? Or in water during the winter time, is because the ice is less dense than the water. So it goes to the top and acts like an insulator to keep the water below it at a high enough temperature that it can maintain its state as a liquid. And that allows life to continue living in there, okay? Water is highly polar, right? We'll talk about that when we get to chapter 8. It's very polar, so it has these electrical properties that are very interesting. It also dissolves compounds into form ions. It also hydrates organic compounds like sugars and alcohols. It's an amazing substance. But here's one aspect of water that's amazing. It can act like an acid under some conditions, and it can act as a base under other conditions. So right here, the water is acting as a base. So here's what happens. You look at the formula and you say, hey, I recognize that as an acid. HCl3 is an acid. That means the water is going to act as a base. Okay. So the acid, it transfers an H plus to the base. So now when you transfer the H plus to the base is now H3O plus. So now you have your hydronium ion. And then what do you have left over? Well, if you lose the H, you have ClO3, but you're not just losing an H, you're losing an H plus. So it's ClO3 minus. And that's aqueous. Anything that, if it has a charge, you're going to write aqueous. So see how that has a charge? So you write aqueous. Okay. Ions are dissolved in water. So in this case, water is acting like a base, but water can also act like an acid, and that's kind of cool too. So for example, let me just show you real quick. This is a base, right? Here what happens is the water transfers the H plus to the base. And so you get NH4 plus and OH minus. So again, think of that water as being H plus OH minus. The water can accept an H plus. So if I take up my water and you combine it with an H plus, you essentially get H3O plus, hydronium. But if you take your water and you take away an H plus, you now have OH minus. So in this case, the water is acting like an acid. It's donating the H plus to the ammonia, so it's an acid. Here, the H plus is getting accepted by the water, so it's acting like a base. So the acid donates the H plus. The base accepts the H plus. And that's what's amazing about water. In this particular reaction, it's acting like a base. In this particular reaction, it's acting like an acid. That's called amphiprotic. Like amphibians, they spend part of their life in the water, in their life cycle, and part of the life cycle on land. That's an amphibian, right? The same is true with water. It's amphi, meaning that it can act like an acid under some conditions, and it can act like a base under other conditions. The protic, meaning acid. Okay, so amphiprotic. So for this one, it's pretty straightforward. You just say, look, I know that's an acid, so I know it's going to donate the H plus to the water. When water gets an H plus, it becomes hydronium, and then the acid is just going to lose the H plus, so it's going to be the polyatomic ion that you have on, combined in the formula. And there you go. Okay. So that's actually ends up being a pretty good intro to acid-base chemistry. Again, we're not really doing calculations with it. You do a lot more analysis in Chem 1200. And then if you go on to take organic chemistry, you kind of come back and you start looking at, the structure of the water and how it's reacting. You're actually looking at the nitty-gritty detail of how the atoms recombine. So how do you get the acid to do this? How do you get the base to do that? That kind of thing. Okay, so you talk about it from that perspective. But right here, we're just mainly identifying and then being able to write the equations for what's happening. Okay, so that's acid-base chemistry. So tomorrow we will do redox. So that's reduction, oxidation. And redox is all about energy. Redox reactions are energetic reactions. So we will talk about that tomorrow. And then there may not be enough time tomorrow to talk about the molarity calculations, the concentration calculations. So I can do those like a little bit shorter amount of time. So I may actually just go ahead and log in on Friday at 9 o'clock and do like an hour-long lecture on the last section, which is the molarity calculations. It's already in the previous semester lecture videos, but I may just go ahead and do that on Friday. I'll let you know for sure tomorrow. But I do want to spend enough time on redox chemistry tomorrow so that you have a good background on that. And then we'll get the molarity done this week. Okay. So have a great day. And then just so you know about the lab reports, like I generally take a while to go through these lab reports. So for those of you that are in the lab, you're actually coming in on Tuesdays, you're going to get full credit. Everybody that came in is going to get full credit for that. So you're going to get, 5 out of 5 on those reports. So don't worry about that. For those of you that are doing the lab reports, distance, thank you for emailing those to me. So I will start going through probably this weekend, grading the first one, which is the calibration of volumetric glassware. So I'll start working on those, and I'll start putting in the grades on those, and you'll start getting some feedback on that probably at the end of the weekend. Okay. So have a great day, and reach out to me if you have any questions or anything. Okay.
Thank you, Dr. Lloyd.
Absolutely. Take care.
Bye, guys.
Bye-bye.